Welcome to our webinar. This webinar it's about the benefits of multitasking your safety critical applications with an industrial grade RTOS. I am Rafael Taubinger, the Global Product Marketing Manager at IAR. I have with me Wellington Durais, the Director of Program Management at PX5.
Rafael, good to be here.
Great, yeah. And also Bill Lamy, the creator of several different RTOS, Nucleus, ThreadX, and latest, the PX5 RTOS.
Hi, everybody.
We are happy to have you with us today. So please notice that you are recording this session, so you'll have the chance to revisit any parts you find especially interesting later. We'll also send a follow-up email with this recording. So we also have a team here available. So for any questions, please make use of the question panels so we can answer any questions. But at the end, we will also cover a live Q&A. So let's get started with the agenda. Here is what we will cover today. I will start with a quick overview of the IAR embedded development solutions and the practical assistance that's available from the tool side. Wellington will then cover the RTOS and functional safety certification, going into details about RTOS, general purpose RTOS or bare metal, timing diagrams, including demo scenarios using IAR, then functional safety certification with the what, why, and how, and also, again, IAR tools in action. We will then finalize with a summary, and we also have a live Q&A. Moving on. IAR Embedded Development Solutions. IAR is the world's leading provider of software for programming processors in embedded systems and offers solutions for developing embedded systems. The solutions support various architectures and are known for their performance and ease of use. The IAR Embedded Workbench. The IAR Embedded Workbench is an integrated development environment. It is known for its debugging capabilities and library support. Support over 15,000 microcontroller devices, ranging from the smallest 8-bit devices to high-performance 64-bit ARM architectures. In total, this includes microcontrollers for more than 70 semiconductor vendors. That's more than any other embedded software tools provider on the market has. And the Embedded Workbench also comes with static analysis code as add-on, supports multi-core debugging, and we also have professional technical support, and very important, of course, it's the functional safety certification that it's available. Implementing the IAR Embedded Workbench, we have the IAR build tools that enables streamlined automated build and test processes in frameworks built on Ubuntu, Red Hat, or Windows. It includes the command line build tools with the compiler, assembler, linker, and the IRC stat. It's also available as add-on, and we support plenty of architectures, including ARM, RISC-V, the Renesas RX, RL78, and RH850, and also microchip AVR. So the IAR build tools are definitely deployable on typical CI environments and supports you on modern workflows. IAR Embedded Workbench and IAR Build Tools Functional Safety Editions. So we have a special edition that is certified by TÜV. It includes long-term support for the special functional safety agreement, and we cover over 10 standards, as you can see, including industrial, automotive, and so on. And we have full flexibility with our support because we support plenty of architectures, again, from ARM to the Renesas architectures and so on. We also have TÜV certified CSTAT for static analysis as add-on, and it's currently available for ARM, RISC-V, and Renesas RL78. So, the practical assistance. IAR offers practical assistance including documentation, tutorials, and customer support. These resources are helpful for troubleshooting and following the best practices to accelerate the certification of your product. IAR Functional Safety Release Cycle. The IAR CC++ compiler has a regular release cycle. These updates provide the latest features and optimizations, important for maintaining the compliance and reliability. But when it comes to the Functional Safety Edition, we release new versions every 12 to 18 months. These releases are then feature frozen, but we still provide some service packs that mainly contains bug fixes. So as you can see here in the image, we have the standard version, and time to time we release new versions, so you can relax, focus on your code while we take care of the certified version. IR also provides a safety guide for developers working on safety-critical applications. This guide covers best practices and compliance requirements, helping you to use the IR tools to meet the safety standards. So it really goes in details and shows you exactly how you should make the tool installation, on how to configure the build environment, some coding considerations, but also library considerations. Definitely, it's really helpful to have a look on the safety guide. And also, IR publishes reports of known issues and their resolutions. This helps you, of course, to stay informed about potential problems and how to address them. So this is, of course, also very important because you need to know if there is any component in the toolchain that might be affected. You get a full description, and of course, it's also listing the workarounds. This information about the regular reports are, of course, also part of the support and update agreement, and you'll get them once a new version or new bug is known that will be sent directly to you. And now over to Wellington, that will show us more about RTOS and functional safety certification.
Okay, I believe I'm sharing my screen now. Okay, so today we'll be talking about real-time operating systems, RTOS, and functional safety certification. We'll run through RTOS, generic purpose RTOS, bare metal. Then I'm going to show some timing diagrams. Then we're going to be running some demos using IAR. Then we jump to functional safety certification, the what, why, and how. And then finally, we'll show some IR tools for functional safety certification. Before diving into the scenarios, we need to make a clear distinction between a general purpose operating system, an RTOS, and the no OS at all approach, as seen here in this diagram. Moving from left to right, what we see here are larger devices in terms of processing power and resources available, moving to smaller ones. A GPOS, like embedded Linux, means we have an OS taking care of the underlying hardware, CPU, timers, registers, memory, network, peripherals, interrupt, you name it. And your application or the device firmware is built on top of the OS and rely on the OS to work. We move to the RTOS, which is a more lightweight solution where we can still count on some support for hardware management, but it is small enough to run on embedded and constrained devices like the ones running on microcontrollers. Another crucial difference here coming from a GPOS is the ability to deal with real-time requirements, situations where the application needs to be deterministic or have a specific time constraint or a deadline which needs to be satisfied. Sometimes RTOS is used on a hardware platform suitable for a GPOS solely because of real-time performance or certification needs. Then finally, we have the bare metal approach, where there's no OS. All hardware aspects are managed by the application or the device firmware, and for simpler applications, this approach might be enough. So let's take a look at this table, where we see that GPOSs are primarily designed for a rich set of services that necessarily require significant amount of memory, typically more than 4 megabytes, and processing power, so typically more than 1 gigahertz. Generic purpose OSs also require hardware memory management unit to support virtual addressing and they're typically not designed for hard real-time requirements. In sharp contrast, an RTOS is capable of operating in memory-constrained environments, in some cases less than 32K of memory, and in addition, an RTOS can efficiently operate on microcontrollers running at speeds less than 48 MHz. And perhaps even more importantly, an RTOS is designed to meet hard real-time requirements, typically in the microsecond arena. So the inability to meet hard real-time requirements pretty much rule out GPOSs from the scenarios I'll be showing next. A typical embedded application runs periodic tasks to process input from peripherals, such as sensors or communication devices, and generate outputs, so send data through communication devices or controls, such as an actuator. With that in mind, let's assume in this scenario 1 an example device that performs machine learning tasks on images taken with this attached camera at every 300 milliseconds. The pseudocode shown here would take care of this scenario. So as we can see here, it's pretty much looking at performing the machine learning task and then taking the time, computing the amount of time spent of the task, and then sleep through the rest of the 300 millisecond window. This timing diagram illustrates how the system behaves. Note that the main task performs the machine learning every 300 milliseconds, and when this task is complete, it goes into idle or low power mode for the remainder of the 300 milliseconds time frame. In this example, a simple bare metal control loop might be enough, thereby eliminating the memory and processing cycles required by a more robust RTOS solution. However, it is important to note that the application code has all the responsibility for allocating processor cycles and meeting any real-time requirements. Okay, let's take a look at the demo. Let me switch to IAR. There you go. This is the first scenario, the super loop scenario. Let me set this one as the active. It already is, so let's run it. Well, as you can see here, I pretty much have the same implementation as in the slide, where we're performing the machine learning, and then we're putting this to sleep for the remainder of the 300 millisecond window. So let me go ahead and run it. There you go. So 300 millisecond time. If I run it again, 600 again. So at every 300 millisecond, we have a proper execution. So again, very simple code, it's easy to achieve what we want here with the super loop. So most embedded systems today can handle more than one periodic task. So in this scenario number 2, let's examine what it looks like as our example device now needs to process 2 periodic tasks. So suppose our device also needs to read the temperature from a temperature sensor at every 200 milliseconds, in addition to the existing 300 millisecond machine learning task. Let's further assume that it's important to read the temperature at fixed intervals. That means the temperature reading has a higher priority over the machine learning task. As you can see by the timing diagram, some of the events should occur concurrently. Specifically, the temperature reading at 50 and 650 milliseconds collide with the machine learning task execution. At the moment t0, down here, the machine learning task is the only one ready to run, so it does. Since we don't have support for preemption at time 50 when we should start running temperature task, but we're already running the machine learning task. So we'll wait until the completion of the machine learning task to run the next one. Of course, this introduces delay or jitter in the temperature task processing. If the real-time requirement doesn't allow for this amount of jitter, the system fails. Let's look at another demo, but then it's important to know that the following demos will have several manufacturer missed deadlines. So deadlines could be missed in a number of other ways. For the purposes of this demo, we're just creating our own. Let's switch back to IR. Now we're going to be looking at the scenario number 2. Okay, and let me run it. As you will see in the scenario, what we're doing here is pretty much performing the machine learning task. And then after that, we're running the read temperature and we're trying to detect if any jitter has happened. And we're counting those. So let me go ahead and run it. There we go, machine learning. So we're up to time 110. Let's do it again, 200. So yeah, at this point, already happened what we were anticipating. So machine learning task was still running. That way, the temperature task had to wait. So that incurs in some jitter. And if I continue running this solution, as you'll see, over time, this jitter count will go up and up. And then again, if this is a real-time requirement that doesn't allow for this amount of jitter, yeah, the system will fail. In addition to the periodic events, an embedded system also handles asynchronous events, typically generated by external interrupts. Now in this scenario 3, let's add a pressure sensor. And when it detects a dangerous high pressure situation, the program invokes a safety task to do something like open a relief valve or something like that. For the sake of this event, let's assume the system must respond to such an event within 10 milliseconds to prevent damage from the pressure buildup. A solution for this scenario implemented without an RTOS could look like this. So we'll have a function to check for periodic tasks, such as the interrupt, which is the highest priority, and a time-based logic to determine if it is time to run the temperature or the machine learning function at specific times. So far, so good. The problem is when we get to the machine learning or the temperature function code. Since we have time deadlines, code for these functions need to keep checking if there's any higher priority function that should be running. And for that, we slice these functionalities like this, here as you can see, between performing a little of that task and then checking again. So do a little machine learning, check for periodic tasks, do it again, check again. Same goes for temperature logic, then do a little temperature logic, check for periodic, temperature logic, check for periodic. So always coming back here to see if there is an interrupt that needs to be considered. This will need to happen in an interval that's smaller than the smallest deadlines we have, in this case, 10 milliseconds. It's needless to say, but I'll say it anyway, that this is a very wasteful process, both in terms of CPU cycles and power. Let's take a look at that. So let me stop IR. I'll move to scenario 3. Let's run it. So now this is running, and as you can see, what we have here in main is pretty much just checking for periodic tasks. The check for periodic tasks will first and foremost check if there is an interrupt for dealing with the pressure sensor. And if not, then there's a bunch of these checking for time, checking if it is time to run machine learning, and then again checking for time and see if it is time to run to read the temperature sensor. So we have a bunch of this time-based logic here. So let's go ahead and execute this for a while. So let's run, and then I'll pause. There you go. So here we have 3.3 seconds run. We got jitter 11 times, and we got 3 safety violations. So this is creating not only an issue for jitter when we consider the deadlines we have for both the temperature function and the machine learning function, but worst of all, at least 3 times here, we had an interrupt to deal with the pressure sensor that were missed because of this whole timing situation. As a result of this run, we see here that we ran this for a little over 3 seconds. We got jitter 11 times, meaning that during this execution, we saw that both the 200 milliseconds for the temperature function and the 300 milliseconds for the machine learning function, we got 11 times we missed those deadlines. But worst of all, we also have safety violations, meaning that the most important one, the safety function, which is the pressure logic, failed to occur within the time frame needed 3 times. Let's now examine what the same example device looks like using an RTOS. With the aid of an RTOS, the example device can be restructured using preemptive programming. The program can be partitioned into 3 threads. So the first thread here is the machine learning thread, the second one is the temperature thread, and the third one, the pressure thread, which is the highest priority one. This pseudocode shows the implementation of the 3 threads, and as I showed in the time diagram, the periodic tasks rely on the timer interrupts to wake them up. Now, unlike the bare metal solution, the threads are not aware of the timing of the other threads, and they don't need to be. Let's take a look at the demo. Let me flip back here, stop IR. Move to the RTOS scenario. Let's run it. So in this sample now, we're using an RTOS, in this case PX5 RTOS. And what we have here is, well, it's pretty much starting the RTOS, creating the threads. We are creating first the machine learning thread, then we create the temperature thread, which is a higher priority. As you can see here that we're setting a higher priority through attributes. And then we have the pressure thread, which is even higher priority. Just like we did before, we are looking for the current time. We are counting the number of jitter. We are counting the number of safety violations and how many times we had the temperature running. So let me go ahead and run this for a couple of seconds. Okay, let me stop. Okay, now we see that we executed this for 6.2 seconds. We got 0 jitter and we got 0 safety violations, even though we run the temperature task 30 times. In summary, an RTOS is generally a better choice than a GPOS for resource-constrained devices or devices that have hard real-time requirements, because the developers can abstract the complexity as the RTOS will manage most of it on their behalf. An RTOS will also enable a divide-to-conquer approach, which will make it easier to manage complexity. An RTOS also enables more features, and developers working on the project There's a potential reduction of overhead when we're eliminating polling and state machines. We can achieve concurrency by enabling other processing when we're waiting for blocking I/O. And it enabled true parallel processing, especially in SMP or symmetric multiprocessing RTOS environments. Now let's get to the critical part. Every missed deadline might pose a risk. In critical applications like automotive, medical, and many others, a missed deadline could be fatal for human lives. And that's why these scenarios require functional safety certification. So, in critical applications requiring functional safety certification, every missed deadline means a functional safety failure. In all these scenarios, a missed deadline could mean a build-up pressure in a boiler, a delay deploying in an airbag, or a cut-off radiation in a medical equipment, so all critical scenarios. So what is functional safety certification? Well, overall, the functional safety certification is a set of guidelines or rules that must be followed so that an application can be certified. Then you apply those guidelines to your product and your process to ensure that you're following them. And finally, you get a certified entity so those folks can independently verify that everything is in order. Usually, it's not. And so there's a cycle of finding and fixes. So there's a cycle here before you get to the end of this process. And then when you get to the end of this process, then you have the certificate along with your certification documentation. So let's take a look at the functional safety certifications around. Here we have a list with the entity, the norm number, and the class, plus the usage. So the first one here is the IEC 61508, and its highest level is the class 4, which is for industrial environments. We also have the ISO 26262 for automotive, the IEC 62304 for medical, and the EN 5128 for rail, where SIL actually means safety integrity level. Now, one of the fastest ways to achieve the high standards required by this industry is to leverage pre-certified parts or components. So in this case here, by leveraging a pre-certified RTOS, you would only have to worry about getting your specific code certified. This will streamline the process to get your product completed. So in this case here, we know the RTOS has been certified in, then let's assume, or for PX5 RTOS case, that's FuSa, the certifying entity, meaning that only the actual code that you're adding would have to be certified before you get the certification. Now, specifically to PX5 RTOS, it can be used in applications requiring the highest level of pretty much all of these four, meaning that PX5 RTOS is certified for industrial at level 4, automotive, ASIL D, medical class C, and rail SIL 4. And how did we get there to the functional certification? Well, we relied exclusively on the IAR development tools for our certification, meaning that we use the IDE, the CSPI, code coverage, the CStat, so all of them that they're coming from the IAR embedded workbench. That means that we now have 100% statement is tested and 100% branch decision has been tested. We have a fully documented development process, and we got the safety manual. We're not getting in this webinar too deep into how to work with these tools, since there are already a couple of previous IR webinars in which this was covered. So I highly recommend you looking at this Hints for Safe C and C++ Functional Safety System webinar by Nicholas and you, Rafael, and also the Safety Guide to Validating Your Application with IR Tools, which is another awesome webinar by Sean Prestridge. So this is a sample of the software integration test report run to PX5 RTOS. And this is one of the 12 documents that we provide to TUV for the certification. The interesting areas in these documents are mostly the graphics provided by the IAR development tools for black box testing, code coverage, and static analysis. Okay, so here is the output for the black box testing, copied from the IAR C-SPI terminal I/O window. And here you can see the list of all of the tests, and then the test results. In this case, yeah, it passes them all. Now, this is the sample of the document that shows the code coverage in the test report, where the names are functions in the PX5 RTOS. And this 100 here means the percentage of code, including branch and decision coverage testing. So in this case, we have all of these functions, all with 100%, and these are all part of the PX5.C code. And here are the results of IAR's CStat, or the static analysis tool, showing no messages or issues here, and here in the PX5 RTOS, other than the claimed exceptions. It's worth noting that the CStat has recently been functional safety certified as well. And what specifically has been certified in the case of PX5 RTOS? Well, in this case, that was the PX5 RTOS generic code, the PX5.C, which is not processor or tool specific, and it does require some assembly code to be certified with the application firmware, which is the PX5 bindings.s. So this must be certified with the application firmware. It contains roughly 10 small assembly language functions, and this is what binds the generic C code of PX5.C to the actual processor and the development tool. Okay, and why should I need certification? Well, as we said before, it's required by several industries like automotive, medical, rail, industrial, and if you're working for any of these scenarios, this is really non-negotiable. But the certification also means improved quality and enhanced reliability. It also means an improved time to market, given that the process is also certified. It means fewer defects, recalls, and reduced product liability. It also represents an overall improved end customer satisfaction. You are pretty much future-proofing your application. And when you're leveraging a certified RTOS, you get all of these benefits even if you don't need the certification. So the artifacts that are provided with PX5 RTOS will be the certificate, the safety manual, the technical report for functional safety, and the certification report for functional safety. Using these safety artifacts, the application does not have to perform any testing on PX5 RTOS generic code. And as a final call to action, let's talk about several of the board evaluation samples for IR that are available at px5rtos.com. Here, as you can see, I brought 4 of them. So the first one is this RISC-V one, which is a RISC-V controller with samples for IAR. We also have several samples for Renesas devices, NXP devices, and ST Micro devices, all with IR samples ready to run. So make sure to visit px5rtos.com and take a look at these samples that are ready to download for free. Okay, Rafael, so I'll stop my presentation here and I leave the audience with my contact information and PX5 RTOS website, where all of you can learn more, get samples, white papers, and know how to get started with PX5 RTOS.
So this then concludes the presentation. Thank you for your attention, and I look forward for having your questions. If there is any additional question or if you need more information, you are welcome to visit ir.com/FuSa or px5rtos.com. Thank you so much.